Okay, now, so welcome back to our discussion of expression evaluation. And now it's time to switch from PostgreSQL to MonetDB. And things look different there. We will see some concept that we have seen in PostgreSQL being carried over to MonetDB, but the actual core of the expression evaluation happens in a completely different fashion, column-wise or vector-wise, as you would expect from MonetDB. And as we will see, this is a mode of evaluation that is particularly well suited to the modern CPUs that we have in all of our computers these days. So expression evaluation really is one of the strong points of the column-oriented database system family, and in particular of MonetDB. This is where MonetDB really shines, and so let's have a closer look at the evaluation of our ProQuery Q6 and what's behind the curtain there. Okay, so it's time to switch over from PostgreSQL, to the MonetDB discussion. We will discuss the evaluation of queries like the Q6 query here. I think the upcoming slides look at a somewhat simpler version of Q6, but still, it's all about expression evaluation in the coming minutes. Okay. Just like other data access operations inside MonetDB, expression evaluation is of course compiled into sequences of mul operations. Okay, and as I told you, just like the normal data access, like table scanning, also the expression evaluation, the evaluation of these scalar expressions, these arithmetic expressions, for example, is also performed in a column-oriented or in a vector-oriented way, and not row by row, as has been the case for PostgreSQL. All of this should be no surprise to you, because of course expression evaluation has to fit with the philosophy of the overall architecture of the column-oriented MonetDB. Okay, and we will see that this is really one of the strong points of the system. Okay, so performing an explain on something that looks like Q6, it's a bit simpler here. You see it's only two expressions, but the points of course still stand. Okay, so performing such an explain on this particular query will yield a mul program as expected, and the mul program will feature some pieces that we have seen so many times already. So for example, the access of the visibility information, which is being held in the ternary but, all right. Then an access to the C column, because the C column is indeed mentioned in the query and will be used for arithmetic expression evaluation. Okay, so let's access the but that represents the C column and then apply the visibility information to the C column. This is what gives us the final column C here. That would be the representation of all the C values inside the C column. All right. We have to perform division by the logarithm of 2 in this query. So we are talking about this sub-expression currently. So the C column has to be divided by the logarithm of 2. The logarithm of 2 is something that could be evaluated at compile time, and that's actually what happens inside MonetDB as well. Just like in PostgreSQL, you see that the logarithm of 2 has been immediately and directly embedded inside the mul program here. No need to evaluate the logarithm of 2 for each of the rows of the table ternary again and again. Now the crucial part is how this division operation is being performed. It's performed on an entire vector of values. The C but here carries all the values in the C column. All of them will be divided by the logarithm of 2 here, and we will get a whole column, a whole but of result values. And you see it will be a but of double values, of double division result values. And we assign that to the temporary val variable E1 here. Okay, so that would be one intermediate result, a whole vector of intermediate results. We then have to perform the ceiling operation, and the same applies to this but math ceiling operation. It will consume an entire vector of intermediate results, and it will compute an entire vector of further intermediate results stored in variable E2 here. That would conclude the evaluation of the expression pointed to right now here. and it would conclude the evaluation for all rows of ternary table T. Okay, so now on to the first expression here, and as you can see, it's referring to the column A. It refers twice to column A. Okay, so these two mal instructions should be well known by now. Retrieve the A column but from the SQL level of MonetDB and apply the visibility information. That's what we've done here. Now in the A but we have the real visible A values of the ternary table. All of them collected in one vector. Okay, we would then perform some casting here. So cast the A values to long values. It's the cast to long operation here for all the A values. All right, this would be our first intermediate result. Okay, then it would be about the multiplication with 3, and I'm talking about this particular sub-expression now. So all of the A values multiplied by 3, and you see this is the task of the batcalc times operation. All of the casted A values, the E3 but will be multiplied by this literal value of 3. It's just represented by a single byte. You see the BTE, the byte type of MonetDB here, or of mal rather. Okay, so what we get there is the first intermediate result. It's the E4 but, and that's the first multiplication performed. The second multiplication is performed, and we store the resulting value in the E5 but, and you see that both of these multiplications refer to the same intermediate result, to the same but E3, which contains the casted TA value. All right, so some sub-expression optimization or elimination is being performed here. We don't compute the casted TA values twice, but refer to the same but twice rather. The final step would be the performing of the subtraction, and of course the E4 and E5 buts would go into this arithmetic operation. And this is the first time that we see an arithmetic operation that operates over 2 buts, over the E4 and O5 buts. How batcalc subtract is actually working on these 2 buts is explained on the upcoming slide. But it's still a whole column operation. So all the E4 values are being all the E5 values are being subtracted from the associated E4 values at the same but offset. This will yield a whole column, a whole vector, a whole but of subtraction results, and E6, the but E6 would be a representation of the resulting column, the resulting column A, the resulting column A of our final result. So all is happening on a column-oriented basis. Okay. The core of the whole thing are, of course, the batcalc routines, in which we have encoded the functionality of all the arithmetic expressions. If you look at the order in which this linear program has been generated by MonetDB, it's just the post order traversal order that we've already considered when we were talking about the linearized interpreter programs that were constructed by PostgreSQL. So this is just the post-order traversal of the expression AST for the arithmetic expressions that are being specified here in the SQL query. Okay, so let's have a closer look at the functionality of this batcalc minus here, the batcalc subtraction. This operator, just like any other arithmetic operator, you see that I've used the replacement algebraic operator symbol here. So this would stand in for the subtraction, multiplication, for addition, and so on. For arithmetic operations in general, they are all implemented inside the batcalc module of MonetDB. Okay. These operations would just merge the tails. The tails, if you recall, are the rightmost columns in the buts. So this operation would just merge the tail, the contents of the tails of the 2 participating buts here. We are performing subtraction, so that's a binary operation. 2 buts are used to provide the input for this binary operation. And these butts are supposed to be synchronized. So the domain of the head column, pointing at the head column now, the domain of the head column is supposed to be identical. So of course, the cardinality of these butts is the same, but they also carry the same entries here in the head column. So we know that the entries at OID 0 and OID 0, those are to be considered the arguments of one subtraction, and indeed we would perform a subtraction on the x0 and y0 value, store the subtraction result under the OID 0 here. And we would do so for all the OIDs that we find in these synchronized butts in which the head domain is identical. So there is no question of which arguments are being considered when we perform the subtraction here in the middle to form the final result. You see that this batcalc routine, of course, contains some handling for arithmetic overflows. We don't see that here in this sketch on the slide. It would perform nil checking and would have some nil logic in there. So if one of the two argument butts contributes a nil value here, we would obtain a nil value in the result. So that's probably what you expect from such a behavior of the batcalc.minus routine. Okay. One more word on the scheduling and the linearization of the operations, of the mul operations inside the program. What we've seen in the mul program on 2 slides back is actually the post order, a post order ordering of the mul operations to implement, for example, the arithmetic expression, the first arithmetic expression in our Q6 query. All right, so a post order traversal would just first access the column A, would then provide the column, the literal value 3, which is easily done using the batcalc times mul operation and inside mul, as you've seen. Then we would perform multiplication before we would turn to the other side of the tree, where we would just perform the multiplication of TA by 2. And once this is done, we are finally ready to perform the subtraction. This is just the post order ordering of operation that you've also seen in the mul program. Of course, there's some potential for parallel evaluation here, because these two subtrees could be considered in parallel. Their evaluation would not impact each other, and we would actually be able to schedule the sequence of mul operations that are concerned with each of these multiplications in parallel. We could spawn several threads on our modern CPUs and have them perform these column-wise operations in parallel. As we see, or as you recall, all of these operations, for example, this multiplication actually is performed on an entire column of A values. So some substantial works actually to be done inside this box, and it would really make sense to spawn a particular thread to have one core of our CPU be focused on the evaluation of this subtree. And the same is, of course, true for the right-hand side subtree. This is a nice source of data parallelism that we could exploit inside our MonetDB system. And there is indeed a particular optimization step inside MonetDB, and an optimization mode, the data flow optimization, that is used to schedule some of the mul operation that we need to perform in parallel. Indeed. Okay. So we haven't seen that on the slide, but this is one option. I just want to mention it, that the strict post-order sequential execution of mul operations is not really a given. Data flow parallelism is actually something that could be exploited here, and is exploited if we enable the particular MonetDB internal optimizations. Okay, so One more word on the internals of this but calc subtract routine, for example. If you recall, we were talking about the generality of the PostgreSQL routines. All of these routines were internally architected to be able to react to all kinds of situations like overflows, nullness, particular types, particular extension being enabled or not enabled. And this would lead to a plethora and a large number of decisions, of runtime decisions that have to be made during the evaluation of arithmetic operations, for example, or the evaluation of arithmetic expressions, rather. Okay, MonetDB takes a different route here and rather prepares very dedicated, very specific routines, tiny C routines that are dedicated to perform just one single task very quickly. All right, so this would be one variant, only one of the many, many variants of the but calc subtract routine that you would find inside MonetDB. It would be the specific version of the but calc minus routine that is prepared to operate on left-hand side but and the right-hand side but. This would be the version of the routine that can indeed scan two argument vectors, two argument buts in parallel, and then perform the synchronized subtraction that we've just talked about. And this will, of course, yield resulting but of subtracted values. As you can see, this routine is also specific and specialized regarding the argument types. This is the version of the routine that consumes and then produces long values. There would be a routine, a variant of the routine that would be specific to the consumption of long values from which we would subtract byte values, for example, or of byte values from which we subtract long values. All of these would be specific particular routines inside MonetDB. Once we have decided that this is the particular routine that is going to be executed, no further decisions regarding types or whatsoever are being made by the routine. Once we enter this routine, the loops that we see that are being performed to do the actual arithmetics are really super tight and simple. This would be the loop that is performed inside MonetDB to perform the actual subtraction. It's a somewhat simplified routine, but it comes close to what actually happens inside MonetDB already. Okay, so it's really a simple for loop that would maintain three indices, three indices I, J, and K. And the I, J, and K indices would iterate over the left and the right and the resulting but, respectively. All right, we would have a very simple ending condition for this loop, because we know about the number of entries, the number of rows, the number of OIDs that we will find in each of these buts. They are synchronized, so the number is the same for all of the input and also for the output buts. And of course, we will advance our indices with each iteration through this loop by 1. All of this is super simple. We would find checking for nil here. So if either the left or the right hand side would contribute a nil at this particular point, the result would be a nil value, of course. We would also write a protocol about the number of nil values that we have found. Maybe it's very interesting for the rest of the evaluation that no nil values have been detected whatsoever. Okay, so if these nil cases are not triggered, then we would just enter the main purpose of this particular loop, which is all about subtraction, of course. So we would use the left and right values at the same offsets. Synchronized buts are the input to this routine. Would just perform subtraction and then store the value in the correct slot in the output but. Okay, and that's all that's going on here. It's really super simple. And the advantages that come with the specification and the compilation and the execution of this super tight, very simple loops is the consequences are very interesting, in particular for modern CPUs. And they are so interesting indeed that we will devote an entire video on these. Actually, I think it's 2 videos. It's really the core of the idea of MonetDB, and I think it deserves a deeper discussion. One final point I want to make here is how specialized these routines are indeed. So we are now looking at the but calc subtract routine that is ready to consume 2 buts here, the left and right buts. I will now switch over to the next slide, and you might miss it. But it's the same but calc minus routine now being engineered to only consume a single literal as its right-hand side argument. We have seen these used also in the iteration of our Q6 query. In the explain program, in the mul program for Q6, you have seen versions of the arithmetic routines that were consuming 2 buts. This is the version we are currently looking at, and the version that consumes 1 but and 1 literal. And I will now switch over the slide to this other variant. Okay, I've switched over. Maybe you've missed it. Back, new version. Back, new version. Okay, so this is indeed the version in which there is only 1 long literal to be consumed on the right hand side. On the left, we still have a but to consume, and you can see that the code for this routine has remains almost unchanged. Everything that has changed actually is these 2 literals here, because there is no right hand side but to walk over. There is actually no need to maintain the j but index, and it's actually not being maintained. As you can see here, we assign the value of 0 to j, and j stays at the value of 0 throughout the entire loop. A clever compiler will just remove the entire presence of the j variable at this time, and it will not be considered at all. It will just be replaced by just the value 0. And of course, this means that we will also, in all iterations, just access the right value itself at index 0, which is the right value itself. So switching back again between these slides, have a closer look at this particular literal here, and this particular literal. Switching back again, these are simply changed and nothing else is different between these 2 routines. This is a consequence of a clever software engineering stint that the MonetDB implementers have taken here. They're actually generating these very specific routines from 1 bit of source code, which is then mangled and passed through multiple stages of pre-processing to yield these very type-specific and these very specific instances of the routines with these super tight loops that process entire columns of input values. Okay, so that's already one taste of expression evaluation inside MonetDB. There is way more to be said regarding this particular topic, and the upcoming 2 videos will do just that. I hope to see you then. Bye bye.